Alright guys, Dr. Colbreth here with chapter 14, number 72. It says, prove that the expression for x of t in equation 14.55 is a solution to the equation of motion for a damped oscillator, which is equation 14.54, if and only if the angular frequency omega is given by the expression in equation 14.56. Alright, well that's a lot of numbered equations. And we really haven't talked about the physics of the damped oscillator. In class, I offered this the position kinematic equation for a damped oscillator, which was equal to a times e to the minus bt over 2m, this exponential decay piece times the oscillating piece, cosine of omega t plus phi 0. Well, where does this come from? That is the purpose of this problem number 72, and I do want to provide a little background information because we are going to set out to prove that this expression, the kinematic equation for a damped oscillator, solves the equation of motion that we get by applying Newton's laws to a damped oscillator. So this is equation 14.55. And let's go ahead and do a little bit of background information. So let's say we have mass on a spring and its equilibrium position is here. And let's consider the condition when the mass is moving to the left. Let's draw right here. Moving to the left, its velocity points to the left. Alright, so in this model, or in this situation, we want to not only model just the spring force, which gives rise to simple harmonic motion, but we also want to consider damping, or a drag force, on our mass. Now we've run into one drag force in Physics 141, and that's the friction force, or the kinetic friction force, which depends on, which always opposes the direction of motion. And so this drag force that we want to write down for this system, we want to also oppose the direction of motion. But the leading cause of drag is not necessarily the friction between the wheels and the cart, or between the mass and the floor, as I've drawn here, but air friction plays an important role, air drag. Okay? And one of the key features of air drag is the faster that you go, the greater drag that you have. So we want our drag force to depend not only on the direction that the object's going, we want the drag force to oppose the motion, but we also want the drag force to be larger when the speed is larger. So we're going to apply the linear drag model. And I want to emphasize that the actual sources of the drag is air drag and friction and maybe internal dissipation within the spring, but the linear drag model is just a model that we can use to approximate these drag forces, and we're going to say that the drag force is equal to minus b times the velocity. Okay, so first of all, we have this feature where the drag force points in the opposite direction that the object is moving. This minus sign tells us that it's moving in the opposite direction of v. The drag force points in the opposite direction of v. And secondly, as we increase the speed, the drag force also increases. And this coefficient b is the same coefficient that we have in our kinematic equations. It's the it is the damping constant. And it depends on both the object and the fluid that it's moving through. So, a big object like a sail, which has a large cross-sectional area, will have a greater drag coefficient than one that has a small cross-sectional area like a bullet. Okay, so B depends on the shape, and it also depends on whether you're in water or in air. Alright, so now we are in a position to do a free body diagram for our mass. We have the spring force, which points to the left. We have the drag force, which opposes the motion, so in this case it points to the right. Normal force, which points up, and the force of gravity, which points down. We've done our free body diagram. Next step is to sum the forces. I'm going to choose in the in the x direction. So we have the spring force, which is going to be minus k times x, and we have the drag force, and we're going to apply our drag model. So this is going to be minus b times vx. And so in the situation we've drawn here, we have that the velocity is pointing to the left, which would be a negative value for the velocity. So this component that points in the x direction would be overall positive, which is consistent with our free body diagram. So this is the sum of the forces. On the right-hand side, we set it equal by Newton's second law towards times the mass, equal to the mass times the acceleration in the x direction. Okay, so now we want to rework this into like an equation of motion, which means we want to get all the terms on one side. So I'm going to move both the bvx and the kx to the other side. We end up with the mass times the acceleration in the acceleration in the x direction, plus b times the velocity in the x direction, plus k times x is all equal to 0. Now we want to rewrite the acceleration and velocity as derivatives, and so we end up with the mass times the second derivative with respect to time of the position, plus b times the first derivative with respect to time of the position, plus k times x is equal to 0. And just to get everything in the same form that we have in the book, I'm going to divide both sides by m, and we end up with the second derivative with respect to time, plus b over m times the first derivative with respect to time of the position, plus k over m times x is all equal to 0. And this is our equation of motion. I'm going to call this equation 1.